Hello everyone, and welcome to my talk about patterns of low latency. So in the P99 conference, we have a lot of interesting talks on specifics of optimizing for low latency. In this talk, I'm going to try to do something different and basically tell you everything you need to know about optimizing for low latency. Just briefly about me, my name is Pekka. I'm the founder CTO at Turso. I previously worked at ScyllaDB and also on the Linux kernel, where I learned much of these latency tricks. The P99 conference template has to have some funny anecdote on P99. So I think P99 happens so often that the conference should actually be called P99.999. The outline of this talk is I'm first going to talk about why latency is important for this crowd. Probably I don't have to do a lot of selling, but I still think it's important to sort of look at the fundamentals, like why do we care? I'm then going to talk about how to measure latency properly, how to reduce latency in cases where you can't reduce latency, how do you hide it, a little bit about tuning the system. It's a big topic of its own, so we're going to briefly talk about it and then basically wrap up the talk. So why is latency important? Low latency means good customer experience, or in converse, bad latency means often unhappy customers. The famous quote on this, or famous findings on this, is from AWS and Google, a decade ago already, where they made this big claim that every 100 milliseconds basically reduces revenue or conversion by some percentage. This is sometimes contested, but I think basically that whenever you're working on applications, you have some latency budget in mind, right? So low latency is essential for good customer experience. And the reality of things is that it's super easy to write code with bad tail latency. And actually many users can experience this bad latency with just one component being having that bad latency essentially. So why is that? Users actually experience tail latency often. And you should really go and read the paper by Dean and Barroso from 2013 called The Tail at Scale. But basically, when we talk about latency, we actually are really interested in something called the tail latency, which is essentially the high percentiles. So for example, the 99th percentile, hence the name P99, of the latency distributions. But because latency compounds, users actually can experience this tail latency fairly often. So you might think that, okay, it's just 1% of the time, but actually because of compounding, it can happen a lot. And one example I'd like to give is if you, for example, have a backend service, which is, taking a user request and then fanning out processing to only 10 components, right? So there could be other backend systems or database queries, but you typically have to wait for all of them to complete. And in this example, if you have 10 components, 9% of user requests will experience the 99th percentile latency. This is what I mean when I say it happens often. The key point is that although the probability of one slow thing is just 1%, actually all it needs to happen is that one of them, so one of those 10 components becomes slow, and then that's basically going to dominate the request processing. So we care about latency because it's essential for customer experience, right? So how do we go about measuring latency? So latency is a distribution, and it means that we need to measure it as such. And oftentimes you hear people talk about average latency, but it's not really an interesting metric. It is essentially the inverse of throughput. And sometimes you hear people talk about the maximum latency, which is a super interesting metric, but on the other hand, it's extremely hard to optimize, right? So if you think about how latency compounds and like all the different components you have in the stack, maximum latency is essentially telling you that worst possible latency outlier, right? So in practice, we tend to take something like the 99th percentile or the 99.99 or percentiles like that, and and it's a good compromise. But when you're measuring for latency, like one really important thing to look out for is something called coordinated omission. And again, like I think you should probably read the blog post by Ivan from 21 on coordinated omission. The original work on this was done by Jill Teen a long time ago already. But basically what coordinated omission means that the benchmark that you use to measure a system accidentally coordinates with the system being measured, right? So what it sort of means in practice is that you actually do not measure the outliers in the latency distribution. So if your benchmarking is doing coordinated omission, it just means that you are basically measuring latency better or seeing better latency than you actually would. And then also visualizing latency is super important. So if it's a distribution and we measure it, so how do we visualize? Like what does latency look like? Histograms are good, but I tend to think that ECDFs can be even better. And this is actually a really great blog post by Mark Brooker on this topic, which you should also go and check out. But just to give you some examples, so here's an example of latency histogram, and I think this is the default HDR histogram, which is a library that you can use when you're benchmarking latency. And this basically just shows you kind of the shape of the latency in a sense. It shows the distribution. So on the y-axis, you have latency in milliseconds, starting from 25 milliseconds, going up to 45 or a little bit beyond. And then on the x-axis, you see the percentiles, right? Then you can see here that, once we get to the 99th percentile, we are a little bit over 45, 40, 46, 47 milliseconds, and that's how it's going to continue up until the 99.99 percentile. But this is super interesting thing to visualize, because now if you think about measuring something like the average latency, so I'm not sure where it would stand out, but you would essentially cut out the interesting part of the tail. But also if you just measure latency once, right, so there's some probability that you will see 30 milliseconds or 40 milliseconds. So that's why it's also important to keep sampling the latency to sort of have this shape of the histogram. But as I mentioned, I actually tend to prefer these ECDFs, which show the exact same information. This is actually a different measurement, I think. No, actually, it looks like the same one. But basically, this is showing the same thing, but in a slightly different way. So now on y-axis, you have the cumulative density. So if we start from the top, it's 1.0, which means all of the latency falls between this area. And then basically on x-axis, you have latency in milliseconds. And this to me looks like a pretty nice latency shape. Sometimes you see essentially that the tail, so that the sort of right part, or the top right part, just ends up being way beyond to 100 milliseconds or more. And this is a cool way, once you start to measure latency as a distribution, visualizing like that, you get a feel of how bad the tail latency essentially is. So that's about measuring latency. Watch out for coordinated omission, measure latency as a distribution, and visualize it. So let's get to the most interesting part, I guess. So reducing latency. So how do we go about, now we know why we care, we know how to measure it. So how do we reduce latency? So key thing, I think, is that latency essentially lurks everywhere. Every part of your stack will have some component that has some variance in latency, and as we know, latency compounds, so they will contribute. I'm claiming basically that there's three main strategies to reducing latency. That's avoiding data movement, avoiding work, and then avoiding waiting. So if we start from avoiding data movement, so moving data is slow. So just few examples, a network round trip from New York to London is at least 57 milliseconds. This is actually, I think, the top of line. You get dedicated connectivity. The reality of things is that, once you start moving data around the public internet, it's going to be a double-digit or three-digit milliseconds just for one round trip, right? And then even in the data center, and these are numbers I just got from some not state-of-art, but high-end network cards, you're still looking at round trip from 100 to hundreds of microseconds. And even accessing something like memory is essentially 100 nanoseconds. So basically this just means that whenever you are moving, or like sometimes you think about accessing data remotely, but in reality you just need to move the data to where you actually are processing it on the CPU or GPU or whatever you're using for compute. So there's essentially a latency lurking there, and there are three main ways to sort of deal with this kind of or avoiding data movement, and that's moving data where it's used with co-location, replication, or caching. So co-location is a technique to just reduce latency by moving two components close to each other. So for example, if you can move the database to the same machine where your application is, something that we, for example, do with SQLite, you essentially eliminate any network round-trip latency. And there's other examples as well, and I think the way this sort of initially caught on was in the high-frequency trading crowd, where they discovered that if you put your machine in the same data center as the exchanges, you reduce network round trip. But co-location is not always possible because you might need this data in multiple places. So it's not possible unless you have multiple copies, taking us to replication and caching. So replication and caching are essentially, from my perspective, co-location techniques that make copies of the data, right? So you can reduce latency not just by moving the data close to you, but just having a copy of the data close to where it's used. And without getting into a lot of details on replication and caching differences, both techniques essentially have their pros and cons around consistency. So how the copy of the data that you're using, can you write to it? If you write to it, like what kind of guarantees you have, and so forth. And also how many different versions of the data can you see, and so forth. But replication and caching, I think, are really great techniques, general purpose techniques to reduce latency if you can deal with the storage amplification. So because we're making copies of the data, we're going to use more storage than with just a single copy. So that's was basically avoiding data movement. So what about avoiding work? So you basically reduce latency by doing less. Less is more. So I picked four main categories of things that you can do to reduce or avoid work. First one is to tame algorithmic complexity. Second one, controlling memory management. Third one, optimizing your code. And then fourth, avoiding CPU intensive computation. So a lot of people hopefully have heard about the big O notation. It just basically tells you how quickly that sort of, or how many steps an algorithm will take as a function of the input, right? So the main thing you really need to understand is that if the algorithm or data structure that you are picking is suitable for low latency. So O1, which means constant time, is probably going to be fine. Of course, it depends on the constant, but oftentimes this is fine. If you have n squared algorithm or worse, it is probably not fine. And these are just rule of thumbs, because sometimes you can have a complex algorithm that's actually in practice very fast because you have small data sets, for example. But just to give you an idea, like what kind of a data structures you're likely to see in low latency code, so queues and stacks often, arrays, except for dynamically allocated arrays, but we'll get to that in a second, and hash tables. You probably won't see a lot of linked lists and graphs in low latency code, because these are typically, or the algorithms that you use to operate on them typically are complex, or have algorithmic complexity. So moving on to controlling memory management. So actually, sometimes I joke about avoiding dynamic memory management essentially being the only thing that matters for low latency. But the thing is that memory management or dynamic memory management ends up being such a dominating factor, especially if you do it in the fast path, right? So when a memory allocator allocates memory or frees memory, there's actually a lot of things it has to do, a lot of interactions with the system as well. So avoid doing dynamic memory management in the fast path. And actually, I have I never forget when I was working on the Linux kernel memory management part, we had a performance regression, and then it ended up showing us a huge network stack performance regression as well. Because basically the way the network stack worked, at least at the time, was like it had to allocate memory all the time for incoming packets and TCP segments and stuff like that. So really, try to build systems that avoid using dynamic memory management. And sometimes people think that if you have a garbage collector, you can do low latency. You can with a pulseless GC, for example, but you still have the same symmetric problem. You need to avoid allocating objects in the fast path, and also did this mistake many times. Second part is to avoid demand paging. So operating systems provide this illusion they call virtual memory, where memory space is as large as disk space. And this illusion works, but it essentially means that virtual memory in the worst case runs at disk speed. So avoid demand paging essentially if you're working on anything low latency. And it's just not just about running at disk speed. It's also about the sort of shift between memory speed and disk speed. So this has really terrible tail latency, and as we know, because of compounding latency, this can become a huge problem. And it's also a problem that's hard to sort of mitigate. Then optimizing your code. I think this is probably the most boring advice on low latency sort of techniques, because this is essentially just, you optimize the code to do less, and therefore you reduce latency. There's typically a lot of sort of ways to improve. So you can reduce the number of CPU cycles you are using, the amount of cache misses, and so forth, right? And this is just the traditional performance work. So find bottlenecks with the profiler, optimize, and keep repeating. But it's also worth sort of remembering that when you're optimizing the code or optimizing to reduce work, avoid doing that at the expense of latency, right? So for example, batching can reduce CPU cycles, so because you can amortize the costs. But this batching can also increase latency, because now you're potentially waiting for a longer time to actually move the work further in a processing pipeline, for example. Then finally, avoid CPU intensive computation. This is probably self-explanatory for a lot of people. But like if you have these long-running CPU intensive computations, they can really hurt latency, because basically you can monopolize the CPU, for example, and other parts of your application won't be able to make any progress. And this kind of has overlap with avoiding waiting, but I decided to include it here, because essentially what you want to do is you just want to avoid these long-running tasks by basically splitting the work. So that was avoiding work. Then finally, when we're reducing latency, what we want to do is we want to avoid waiting. And there's, again, I think 4 main things to look out for. So one of them, or do one of them, the first one is to eliminate synchronization. In cases where you cannot eliminate synchronization, you want to use wait-free synchronization. Then also you shouldn't be waiting for the operating system, and also not waiting for the network. So synchronization, this is for low latency code, this is a major topic. So basically synchronization with mutual exclusion means threads have to wait. So the basics of mutual exclusion is that you have this mechanism which allows only one thread to operate on a critical section, like a piece of code that is changing shared state, for example. And there's a lot of this is basically just multi-threaded programming stuff. There are a lot of things that you should do if you have to use synchronization, like keep the critical sections as short as possible. But basically, this is always going to be a sort of source of latency, and plausibly a major source of latency. So what you do is you partition data to eliminate synchronization. And this is one of the reasons why thread per core architectures are so unreasonably effective, is because essentially CPUs run independently of each other. Like no threads are going to wait for anything. Every core will just go full steam ahead. But also, one way to eliminate synchronization is to make shared data structures read only when possible, right? So, in cases where you don't actually have to modify the data, you just make it read only. And there's stuff like a read copy update and things like that to optimize cases where you just sometimes write to it. But basically, to reduce latency, eliminate synchronization when possible. And in cases where you cannot eliminate synchronization, and this is I think most systems will have some shared state. Use wait-free synchronization, right? And just at super high level, what wait-free essentially means is that every operation has finite number of steps and no waiting. And this is great for low latency. It's often super hard to implement, but it basically means that now you have some kind of bounds on essentially every operation that you do, and now you kind of things might even run more slowly than with synchronization in some cases, but at least you have sort of consistency in terms of the latency. So now you're kind of eliminating the unpredictable tail of it. And the main example here is single producer, single consumer queues, which are relatively easy to implement, and lots of good examples are out there. And these are like a great low-level primitive for low latency request processing. So even in thread per core architectures, for example, you sometimes need to steer request between or basically move request processing from one core to another if you have the data partitioned. So these single producer, single consumer queues are super fast, fairly easy to sort of prove to be correct, and you can use this as a kind of low-level primitive sort of work queues and things like that. Then just moving, sort of wrapping up the avoiding waiting stuff. So you shouldn't wait for the operating system. So some sort of rules of thumbs as well. So you should avoid context switching. So don't create too many threads. Be easy on the system calls. This can easily create tail latency in any application. Also use non-blocking I/O. For example, I/O U-ring or even Linux AIO interfaces are pretty good with this. Essentially, blocking a kernel thread on I/O is more or less guaranteed bad tail latency at any eventually at least. Then maybe slightly counterintuitive, but you can also use busy polling, especially if energy is not a concern, because sometimes it's faster to just poll for an event, like just have the CPU busy polling on something rather than waiting for it, because waiting actually is surprisingly expensive. It will involve context switching, it will involve the kernel scheduling and so forth. So busy polling is often an interesting way to avoid waiting to reduce latency. And then finally, you can also try to bypass the kernel completely if you can. So for example, XDP and DPDK provide ways essentially to run the network stack in your application. And this sort of opens up a lot of possibilities again for avoiding waiting the operating system to do things. Then finally, don't wait for the network. So it's also always TCP no delay or lack of it that's causing your latency problem. So actually, maybe this should be the first one before avoiding dynamic memory allocation. But you should disable Nagel's algorithm essentially. Then also avoid head of line blocking. So if you have a lot big requests coming in the queue and taking a long time to process, this will basically slow everyone down. So avoid that as well. So now we talked about why latency is important, how to measure latency, how can we reduce latency by avoiding avoiding waiting. So how do we go, like if we can't really do any of this optimization, so how do we go about hiding latency? So first trick you can always do is you can parallelize. So in cases where something is simply, it's just going to take time to like process a request, for example. A good way is to reduce latency is to essentially parallelize it. So in the example we're looking at in the beginning of this talk on a REST API or something like that, which fans out request processing to 10 different backend systems or just database queries. So if you can, you should just do all of those fan outs in parallel, because now it means that you don't have to wait for each one of them individually. You will just wait for the slowest ones, because otherwise other ones essentially once completed, you will have the result. So parallelizing request processing is a great way to hide latency. It doesn't really fix the latency, but can go a long way. Kind of a related optimization or technique is hedging requests. So in cases where you can send the request to multiple servers, so if you have a distributed key value store or a database or something like that, with multiple copies of the data, so you send the request to multiple servers and just use results from the fastest one. And this is actually also something from the tail at scale paper I mentioned in earlier part of this talk. And then finally, lightweight threads. So for example, GPUs high latency by just executing massive amounts of lightweight threads in parallel, which hides memory access latency. That's, I guess, that the main trick why GPUs go so fast. But basically, you can apply this kind of a approach also in user space. The thing you need to really just keep in mind is that kernel threads are not lightweight. They are extremely heavyweight, because you end up doing the scheduling on all of that in the kernel. So that's why I added this sort of difference of lightweight threads. So that was about hiding latency. Then finally, just have a really brief look at like tuning the system. So what kind of things you can do just by essentially configuration. So the first and probably most obvious one is to configure something called CPU frequency scaling. So CPUs tend to scale down their frequency to reduce energy consumption. So for a low latency system, typically this is this is oftentimes, especially if you're doing some latency measurements on your laptop, this is typically what you sort of observe first, so that the CPU sometimes goes faster, sometimes goes slower. So just configure it to be whatever sort of makes sense from your application or workload perspective. So sometimes you just make it, you tune it to be, configure it to be, performance, which means that it will just run all out. Actually, there's a funny thing that I think some Intel CPUs actually overclock themselves in some scenarios. So even then you were not kind of safe. So sometimes the CPU would go faster even if you configure it to go at constant frequency. Then a big one is to isolate CPUs for application threads, or you could say the same thing for isolating for kernel threads. So this is maybe something people don't find, or this is not obvious to people oftentimes. So the operating system has a lot of background threads, like the network stack has background threads, and you have the soft interrupts and things like that. So to avoid latency variance in your application threads, and for example, if you have a thread per core architecture, this becomes kind of critical. So you want to isolate some CPUs for the threads that you use in your application and just leave enough capacity for the operating system. Kind of related to demand paging, so disable swap. So what swap does is essentially moves unused or less used memory into disk, and essentially has the same, maybe even worse characteristics as demand paging. So sometimes your application just runs extremely slowly. So disable swap if you're willing for low latency, and then also configure network stack interrupt affinity. Kind of related to isolating CPUs for application threads, but even a bit more specific. So when packets arrive from the network to the NIC, that some CPU will process them, and Linux has this configuration where you can basically say that, okay, given these types of packets, process them on this thread, on this cores and so forth. So this can also be a significant sort of source of latency. So when you're tuning the system, this is something to really keep in mind as well. So now, we know why we're measuring latency. So why latency is important, how to measure it, how to reduce it, how to hide latency, and then how to tune the system. So to wrap up, latency is a distribution, so you should measure and visualize it as such, and also watch out for coordinated omission. To reduce the latency, just avoid data movement, avoid work, and avoid waiting, and you get pretty far. When you can't reduce latency, try to hide it with the tricks that we mentioned about with parallelization, for example, and request hedging. And then finally, tune your system for low latency. And if you felt that I, maybe left out some small minor details from this talk to fit it in this time frame, I'm actually also writing a book on this. It's actually on Manning Early Access. And for you P99 conference attendees, you can get 50% discount with this P99 2024 code if you go to their online store. So that's it. Thank you everyone for participating.